Hi, my name is Naren, and today I will tell you about our paper that will appear at STOC 2024 titled Near Optimal Streaming Ellipsoidal Rounding for General Convex Polytopes. This is joint work with my advisor, Professor Yuri Makarisha, and my lab mate, Max Osiankin. So in this talk, I will briefly go over the motivation and the problem statements that we study in this paper. I will then go over a sketch of our results, and then I will tell you a little bit about the algorithmic ideas that we give, along with a rough sense of how we analyze them. So one of the main problems that we study in this paper is that of ellipsoidal approximations. So here, let's think of Z as being the convex hull of the points Z1 through Zn, each of which lies in D dimensions, or you can maybe picture the thing on the right. And here we'll say that E, the blue outer ellipse, is a 1 over alpha approximation to Z. By this, we mean that E covers Z, and alpha times E also lives inside Z. So here, let's always think of alpha as being less than 1. So all the approximation factors that we describe are going to be at least 1. So why might you be interested in finding ellipsoidal approximations? Well, one rather natural application is that it gives us an affine transformation that we can then use to precondition a convex body for some downstream task. So in other words, it places the convex body into a position where it's not too long in any one direction. It's not too short in any one direction either. It also will allow us to construct convex hull core sets, which is an application and a concept that I will describe in the next slide. And more generally, it allows us to succinctly summarize a convex body. So let's imagine the case where n is much bigger than d, and we wanted to write down some description of z. So writing down z to full fidelity might require us to write down all the endpoints, and this requires us to actually write down n times d many floating point numbers. But instead, if we had this ellipsoid E, then at least up to this 1 over alpha approximation, we could write down just d squared many floating point numbers and geometrically summarize z. So one way to at least write down an ellipsoid with d squared many floating point numbers is to just write down all the semi-axes of the ellipsoid along with their lengths. And before we ask these algorithmic questions about how to find these ellipsoids, let's at least get a sense of what existentially can be done. So we have a sense of what sorts of approximation factors one might expect. So a famous result due to John from 1948 tells us that one can always get a factor d approximation simply by taking the minimum volume outer ellipsoid of the convex set Z. So this always gives a factor d approximation. And moreover, this is worst case optimal in the sense that there exist convex bodies for which any ellipsoidal approximation must get a factor d, so such as the simplex in d dimensions. So now let's take a look at the convex hull core set problem that I mentioned briefly in the earlier slide. So here we'll always write Z restricted onto S, or Z bar S, as the convex hull of the points Zi, such that I is an S. So let's take the picture on the right and see what this looks like. So let's say we have this convex set Z, and maybe we look at these starred points in blue here, and look at the convex hull of that and a rescaled version of it. So here, again, similar to the previous slide, we'll say that Z restricted onto S is a 1 over alpha approximation to Z. So why might you be interested in finding these convex hull core sets? Well, one application is, again, you can succinctly summarize a convex body up to this approximation factor. So in particular, if you manage to make the size of S rather small, then you would get a pretty short summary of what, at least a short geometric summary of what Z looks like. It also gives us a formal sense in which we can determine an important subset of the convex body, meaning that the points that belong to S were in some sense the points that contributed the most to the geometry of Z in a particular sense. Okay, so now let's take a look at the streaming versions of these problems, which is what we study in this paper. So in the streaming version of the problem, we're going to be given streaming access to Z. So we're going to see the points Z1 through Zn one at a time, and we get one pass over Z1 through Zn. And the goal is to give an algorithm that will output a 1 over alpha approximation. So we want to output a point C, a scale alpha, and an origin-centered ellipsoid E, such that alpha times E shifted by C lives inside Z, and also E shifted by C covers Z. So just always keep in mind the picture on the bottom left. So in addition to studying the ellipsoidal approximation problem, the streaming constraint allows us to encode this idea that the input might be too large to store in memory. So if we're trying to produce a summary of a very large data set, then it's conceivable that this input itself is just too large to fit in memory. But in the streaming model, we are still able to access Z, just not all at once. So we're going to see these points one at a time in the order 1 through n. And similarly, we can look at this online convex Hull core set problem, where again, we're given streaming access to Z, and the goal is to output some subset S and some centers C, such that the following approximation guarantee holds. Okay. So now, before we go into the results that we give for this work, let's take a look at what prior work says about these problems. So prior work studies the case where the convex set Z is origin symmetric. So in this setting, and for the streaming ellipsoidal rounding problem, work due to Woodruff and Yasuda and work due to our group give the following approximation and runtime, and memory complexity guarantees. So our work gives a square root d log kappa approximation, where kappa is an aspect ratio term that I'll describe in a moment, and has d squared memory complexity. Importantly, this memory complexity does not depend on the number of points n that we see so far, or that we see in the entire stream. So similarly, Woodruff and Yasuda give a similar approximation guarantee with a slightly different term inside the log factor. So it's an n times an online version of this aspect ratio term, though their setting is very slightly different from the one that we studied earlier. But also it gives d squared memory complexity. So importantly, the memory complexity that they also give does not depend on the length of the stream. And similarly, for the online convex Hull core set problem, the same work due to Woodruff and Yasuda gives an algorithm that chooses a subset whose size is d log n times this online aspect ratio and gives the square root of that approximation factor. So just a few remarks are in order here. So I introduced these terms kappa and kappa OL. Let's always think of these as maybe representing the condition numbers of the convex set, or a matrix associated with the convex set, or the aspect ratio of the convex set. So it encodes in some sense how stretched out or how oblong the convex body that we're considering is. And moreover, the work of Woodruff and Yasuda is able to replace this online aspect ratio term with an n when the vectors have integer entries that are bounded by this polynomial net. So that means they can make their results condition number independent or aspect ratio independent. In any case, all these prior work studied the symmetric case only, where z was equal to minus c. But remember that in the problem statement that I said earlier, that no such assumption was made. So what happens to be to handle the more general asymmetric case? And then finally, one more remark is in order. So remember that by John's theorem, I stated earlier that there, at least in the worst case, one cannot hope to do better than a factor d approximation. But here, these approximation guarantees have a square root d dependence. And this is because John's theorem actually gives an improvement when the set is symmetric. So in particular, the minimum volume outer ellipsoid for a symmetric convex set will always give a square root d approximation. Okay, so now that we've just summarized the motivation in the problem statements and some of the landscape of existing work, let's take a look at what our results in this paper look like. So in what follows, let's just let capital R be the radius of the smallest Euclidean ball containing Z. And now let me describe the first result that we get. So if you're following along in the paper, this is basically a summary of theorem 1. So again, we're given streaming access to the points Z1 through Zn. So we're seeing these points one at a time in this order. And we're also going to be given a ball of radius R0 that lives inside Z. So the result that we get in this setting is a streaming online algorithm that will output a center Cn, a scaling alpha n, and an origin-centered ellipsoid En, such that alpha times En shifted by Cn lives inside Z, and also En shifted by Cn covers Z. So just use the picture on the right to help map things. And the approximation factor that we get here is 1 over alpha n is essentially this d log aspect ratio term. So here it should be clear why you can think of R over R0 as an aspect ratio. So the runtime of this algorithm is about nd squared. So it takes about d squared runtime per point, and it has a space complexity of about d squared. So importantly, the space complexity does not depend again on the length of the stream n. So now a few remarks are in order to describe this result. So first is about this initialization assumption, that you're given a ball of radius r0 that is contained within Z. Well, we show that this initialization assumption is not strictly necessary, but so you can do away with it, but you get a slightly different approximation guarantee that has a slightly worse aspect ratio dependence. Moreover, if all the coordinates are integers that lie between minus capital N and positive capital N, then one can get an aspect ratio independent result. One can in fact get a d log d times capital N approximation guarantee. So that's theorem 3 in the paper if you're following along. And moreover, notice that again by John's theorem, it says that one could get a factor d approximation, at least existentially. But we have this extra multiplicative log aspect ratio term. So a natural question to ask is whether this is necessary in the models that we study. And we answer this question affirmatively for any class of natural algorithms that we call monotone algorithms. I'll describe this in a moment, but this is theorem 5. Finally, one more remark is in order. The runtime that we get, nd squared, is competitive with the best known runtimes for offline versions of this problem. So we're really not losing much by imposing the streaming model, at least as far as this problem is concerned. And then for the online convex hull core set problem, we get analogous results. So as usual, we're given streaming access to Z1 through Zn. And the result that we get is a streaming/online algorithm that maintains a set ST such that at every time step t, we maintain this approximation guarantee. So we maintain a CT, an ST, and an alpha t such that this guarantee always holds. The approximation factor is the same as essentially the same as it was previously, and the runtime and the space complexity are the same. So just remember that the space complexity here does not depend on the stream length n. And then as before, if all the coordinates are integers in minus capital N up to positive capital N, then we can replace all the condition number dependencies with a capital N. Okay, and if you're following along in the paper, this graph here might help visualize where the results get used throughout the paper. So theorem 2 will follow from theorem 1 plus a few extra steps. Theorem 3 takes theorem 2 and a few extra ingredients. Theorem 4 is a combination of theorems 2 and 3 along with a few extra ingredients and steps. And then theorem 5 can be taken as separate from all of the above. All right, so now let's go over some of the algorithmic ideas and the ideas behind the analysis of these algorithms. So the first thing that I want to talk about here is the notion of a monotone algorithm. So I briefly mentioned this on the results slide. So now we'll go into more detail about this. So let's think about the following setup. So let's say that our algorithm is only going to track two ellipsoids, an inner ellipsoid and an outer ellipsoid. And it's always going to enforce that the inner ellipsoid lives inside the convex hull of the point seen so far, and the outer ellipsoid always lies outside the convex hull of the point seen so far. But we do not store any points that we've seen previously. So now we can ask the question, what should we enforce what sorts of set containments should we enforce that our next updates obey? Well, let's draw a picture out and see what these containments could look like. So let's think of the blue circles as the outer and inner ellipsoids at a particular time step, and the red point as a new point that we're seeing. One thing that we can definitely say is that the new outer ellipsoid must cover the old ellipsoid and the new point. So in other words, it must cover the convex hull of the outer blue ellipse in this picture, the two black lines, and the red point. So in particular, the orange outer ellipse is a valid update according to these constraints. Now, the new inner ellipsoid constraint is a little bit more technical to describe, but it's not too hard to see from the picture. So if we're not tracking any of the points that we've seen up to this time step, then it's necessary to enforce that the new inner ellipsoid lives inside the convex hull of the old inner ellipsoid and the new point. So in this picture, it's the convex hull of the inner blue ellipse, the two purple lines, and the red point. So as long as we manage to design an update rule such that the new inner ellipsoid lies as is shown in the picture, then we will always obey the invariant that the pair of ellipsoids that we maintain will always inscribe and circumscribe the convex hull of the points that we've seen. So now any algorithm that obeys these invariants, we'll call this a monotone algorithm. It's easy to see by an induction argument that this will output a feasible solution, meaning that at the very end, the pair of ellipsoids will inscribe and circumscribe the convex hull of the points that lived in the stream. So with all this in hand, it's not enough to find a monotone algorithm such that the evolution of its approximation factor is something reasonable that we can handle. And that's the subject of the next slide. So here, just think of this picture as representing this, like a valid monotone update, according to the previous slide. So we're going to enforce that our updates satisfy this evolution condition, which is essentially a bound on the change in approximation factor at time step t. So here, delta alpha t plus 1 represents the change in approximation factor that we get when we add in point t plus 1. And let's say that we manage to design an update rule, a monotone update rule, that obeys this, this invariant over here. Then, in fact, this is enough to get a decent approximation factor. And let's see how this works. So let's just first write down the following difference here. Let's pretend that alpha 0 is equal to 1 for now. So this can be written as the sum of all the changes in approximation factors starting at t equals 0 up to n minus 1. Which is then, you can plug it into the formula from the dashed box above. It's at most the log, the ratio of the volume of the final outer ellipsoid to the initial outer ellipsoid. And then using the fact that the final convex hull lived inside a Euclidean ball whose radius was capital R, and a quick bootstrapping argument, you get the following approximation guarantee on the right. And note that there's a dangling extra dimension factor inside the log, but this can be handled. So what we see from this is that if we are able to design a monotone update rule that obeys this evolution condition, then we get a respectable approximation factor. So now what remains is to design an update rule that does in fact satisfy this evolution condition and is monotone. And so that's what we describe in this slide. So let's first take a look at some reduced two-dimensional case. So by an affine invariance and symmetrization type argument, it's enough to look at a two-dimensional case where your current ellipsoids are Euclidean balls. So let's again keep in mind this picture here on the right. And the intuition for deriving our update can be written as follows. So suppose that the new point that we see is actually arbitrarily close to our current outer ellipsoid E. Now let's look at an ellipsoid E prime that passes through Z and is tangent to E at, let's say, 2 points. And if you carefully choose where the tangent Z points are, then we can actually control the approximation factor. And now we repeat this as we drag Z back out in increments back to its original position. So here, let's see what this could look like if we wanted to discretize the update Z into 3 steps. So here we start out with the original black circle, which is our original black outer ellipse. Now we add this point here and enforce that our new solution passes through this discretized version of Z and is tangent to the old solution. And we stack these updates. And one can then consider taking the gap between these consecutive updates very close to 0, and then considering some approximate limit of this process. You then repeat and then get some update at the very end that is can be approximately analyzed. And the important thing to note here is that this gives a rank 1 update. So this can be implemented very efficiently in just a constant number of matrix vector multiplies. So one thing to remark here is that this family of updates can be characterized, but the minimum volume ellipsoid that passes through Z and covers your old solution might actually yield a very suboptimal approximation factor. Now let's take a look at how we take our ellipsoidal approximation algorithms and design these convex hull core set subset selection algorithms from those. So the very high level idea is to maintain an ellipsoidal approximation as the internal state of the algorithm and look at the points that cause the biggest change in this in this internal state, which can be always thought of as the most important points that we've seen so far. So as usual, remember the condition that we are enforcing our algorithms satisfy, our ellipsoidal approximation algorithms. And the update rule can then be translated from the idea as follows. So if the volume of the outer ellipsoid grows by a sufficiently large constant, or if the new point that we see is affine independent from the points we've seen previously, so you can think of this as moving into a new dimension, then we add that point to our set S. So that's the subset selection rule. And in order to analyze this, we have to prove two things. We have to prove that we don't choose too many points, so the size of the core set is small. And then we have to show that the convex hull of the subset that we choose is a respectable approximation to the convex hull of the whole set. So showing that the core set size is small is a pretty straightforward task. So we know that from previously, the approximation factor of the ellipsoidal update rule is pretty small. And so if we're only choosing the points that basically cause a very large change in the approximation factor, and the total approximation factor was pretty small, then we couldn't have chosen that many points. Now, to analyze the approximation factor, we follow the following framework. So first, you take the contrapositive of the update rule, and then it's easy from there to conclude that some rescaling, some constant rescaling of the ellipsoid at time t will cover all the points that we didn't add to the core set. Which then means that the output of the ellipsoidal approximation algorithm, if you ran it on just a subset, looks pretty similar to what you would have gotten had you run it on all the points from 1 through n. And then if the same ellipsoid is a decent approximation to both z and z restricted onto S, then you can use this to show that z restricted onto S must be a decent approximation to z itself. So translating all of this intuition into math will give a working analysis. So one thing to remark is that this subset selection rule, in some sense, generalizes the online leverage score thresholding algorithm that Woodruff and Yasuda use to give their convex hull core sets in the symmetric case. So in particular, we can think of this delta alpha t plus 1 as some asymmetric variant of the online leverage score at time t. So that's all I had time for. Thank you very much for watching, and I hope to see you at the conference.